All right, welcome. In this lesson, we're going to talk about alternating series. We're going to look at a test to see if an alternating series converges or not. We're going to look at two different types of convergence, and we're also going to look at estimating the series, the sum of alternating series to a certain agreed upon error. So let's start here with what is an alternating series. An alternating series is a series whose terms are alternately positive and negative on consecutive terms. So you'll see plus, minus, or minus, plus, repeated throughout the whole series. Okay, we've got some examples. We've got lists. We've got our sigma notation. Notice that each of our sigma notations or each of our lists has that minus plus or plus minus. It doesn't matter which one comes first. And each of our sigmas have this kind of alternating factor, alternating part, or alternator, where you've got a negative value raised to a power, and that power changes, kind of like a switch, turns on and off. Even power is positive, odd power is negative. So in general, just knowing that the limit as n approaches infinity of a sub n equals 0 tells us very little about the convergence of the series. However, it turns out that an alternating series must converge if its terms consistently shrink in size to 0. Okay, so our alternating series test. All right, we'll abbreviate it AST. It says if a sub n is greater than 0, then the alternating series alternating series from 1 to infinity of negative 1 to the n a sub n, or the infinite series of negative 1 to the n plus 1 times a sub n converges if both of the following conditions are satisfied. All right, so notice that we've got this alternating part here, and then we've got this kind of the rest of the rule, a sub n. So that's what we're looking at here, the rest of the rule. If both of these things are satisfied, so if the limit as n approaches infinity of the rest of that rule equals 0, and if that a sub n, rest of that rule, as terms in the sequence is a decreasing or non-increasing sequence. That is, if a sub n plus 1, the next term, is less than or equal to a sub n for all n greater than k for some k where k is an element of all integers. All right, so again, it's just saying at some point along the line, it's a decreasing sequence. It doesn't have to start right there at 1, but at some point it decreases for the remainder of the sequence. All right, note, this does not say that if the limit as n approaches infinity of a sub n does not equal 0, the series diverges by AST. AST can only be used to prove convergence. All right, the limit as n approaches infinity of a sub n does not equal 0, then the series diverges not by the AST, but by the nth term test. All right, so keep that in mind. We're never going to use AST to show divergence. All right, it may be a step along the way, but it won't be the reason to show divergence. All right, example 1, determine whether the following series converge or diverge. We'll do a couple of these together, and then I want you to work out some of these on your own. All right, part A. All right, we've got the infinite series of negative 1 to the n plus 1 times n over 2n minus 1. Again, it's going to be important to pick out that alternator. Because that's going to show that this is indeed an alternating series. All right, can't use the AST if we don't acknowledge and state that it's an alternating series. All right, so when we see that, now what we want to do is we want to look at this first part. All right, and show that the limit as n approaches infinity of the rest of the rule equals 0. All right, so we're going to say the limit as n approaches infinity of the rest. So we have an n left in the numerator and 2n minus 1 in the denominator. All right, so as n approaches infinity, so looking at our n behavior model, we've got n over 2n minus 1 doesn't hold its own weight, so we're going to have a 1/2. All right, 1/2 is not 0. All right, since it's not 0, we can't use AST. All right, so since the limit doesn't equal 0, we can say that our series diverges, not by the AST, but by the nth term test. All right, part B. We've got the infinite series of -1 to the n times n. All right, same numerator, almost same numerator, over natural log of 2n. All right, so again, pick out that alternator. Yep. I'm a good speller. All right, so that means that we have an alternating series. All right, so let's see if we can use the AST. So we want to look at the limit as n approaches infinity of the rest of that rule. So we've got n over natural log of 2n. Okay, so we've got linear on the top. We've got a natural log with a 2n in the denominator. We want to find the limit as n approaches infinity. So this looks like a good L'Hopital rule, because if we plug in infinity in both, we're going to get natural log of blah, 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 that's going to be infinity. All right, so L'Hopital's rule says we take the derivative of the top and the bottom. Derivative of n is 1. Derivative of natural log is 1 over stuff on the inside times the derivative of the inside. All right, so we're taking the limit of that. Let's see, 1 over 2n times 2. Those 2's are going to go away. 2 over 2 is 1. So we're just left with 1 over n, which is just n. So as n approaches infinity, that's going to approach infinity. That is also not equal to 0. All right, so over 2. We can't use AST here either. But since the rest of our function there the limit as n approaches infinity went to infinity, then we can say that our series diverges by the nth term test. All right, part C, our infinite series of cosine of n pi over n. All right, notice this one doesn't have that -1 to a changing power, but it does have a cosine. Remember, cosine alternates between positive and negative, so we're going to treat this as our alternator. All right, so that shows that we do have alternating series. So let's give our AST another shot. Third time's a charm. We're going to take the limit as n approaches infinity of the rest of our functions. So nothing left in the numerator, just a factor of 1 and n in the denominator. All right, as that denominator grows without bound, the value of that whole piece goes to 0. Boom, that's what we were looking for. All right, so those values are going to continue to decrease over time. So first piece, let's go back up to our AST. First piece, check. It is decreasing over time. So we have part C. We have convergence by the AST. All right. Let's do one more together. Part D. Okay, we've got the infinite series of -1 to the n minus 1 over n factorial. Okay, so again, keep your eyes out for those alternators because after this is it for our convergence tests. So from this point forward, these types of infinite series are not going to be split up into this type of test and this type of test. You're going to need to be able to look at these series and acknowledge which test is going to be used for, or at least try one. If it fails, try another one. All right, for the AST, you got to be able to pick out that alternator. So when you see that, it is a good sign to try the alternating series test. Okay, so let's look at the limit as n approaches infinity of what's left. So just a 1 left in the numerator. We have n factorial in the denominator. So again, as n approaches infinity, that denominator is going to grow bigger and bigger and bigger, which leads our value of our fraction to go to 0. So that means another winner, converge is, or convergent by AST. Okay, if you would, in your notes, try parts E and F, and we'll talk about those next time we meet. Okay, next up, absolute versus conditional convergence. If the series from 1 to infinity of the absolute value of a of n converges, then the infinite series of just plain old a of n also converges. All right, so such a series is called absolutely convergent. Okay, so now we're kind of splitting up converging into two types of converging. We've got absolutely convergent. All right, so notice that if it converges on its own, the alternator only allows it to converge more rapidly. Now, we kind of changed what our a sub n means here. This is like the whole rule with the alternator inside of it. Same thing for this a sub n. So this absolute value just kind of negates or flattens out the alternator, so that's not really doing anything. And this is with the alternator included in it. Okay, so it says, notice that if it converges on its own, the alternator only allows it to converge more rapidly. All right, next up, our infinite series from 1 to infinity of a sub n is conditionally convergent. If the infinite series of a sub n converges, but the infinite series of the absolute value of a sub n diverges. All right, so if you flatten out, remove the effect of that alternator, and that series diverges with it in there, converges, and it is conditionally convergent. All right, so it's conditional on that alternator to converge. Okay, so let's look at how we're going to do this. Now, because there are essentially 3 outcomes now, so we've got 2 types of convergent, absolutely and conditional, and we have divergent, then we're going to have kind of 3 situations we need to keep our eyes out for. All right, so if we're doing ourselves a favor, then we're going to check for absolute convergence first. All right, if it converges, we can stop. The series converges absolutely. All right, if it doesn't, then we're down to either conditional convergence or divergence. All right, so if the series does not converge absolutely, check for conditional convergence with the alternating series test. If it converges, the series converges conditionally. If it doesn't, then the series diverges. Make sure you jot these down in your notes You could even make yourself a little flowchart, that's your thing. But again, 3 outcomes here. Let's see what a couple examples are going to look like. Example 2 said determine whether the following alternating series converge absolutely, conditionally, or diverges. All right, first one, we got an infinite series of -1 to the n over the square root of n. Okay, so we always want to check for our absolute convergence first. So let us find the infinite series. So n equals 1 to infinity of the absolute value. It's a -1. Let's try that again. Okay. So again, if this one converges, then the original up above it also has to converge. We're done. We kind of essentially didn't need to check that first one. But if it doesn't, then we will need to check it and see if it either diverges or is conditionally convergent. All right, so if we take the absolute value of this, then this is the same as if we took out that alternator there. All right, so here's our alternating piece there. If we take the absolute value, it has no effect. So we're left with 1 over root n. All right, so root n is the same as n to the 1/2. So that looks like a p-series to me. P-series, P-S-E. Look at the speller. P-series. Then let's see, what is our P? Our P is 1/2. Absolute value of 1/2. We don't need to do absolute values less than or equal to 1. All right, that means that if it's less than 1, then it's going to diverge. All right, by the P-series test. All right, so we know it's not absolute convergence. All right, that would need to converge for it to be absolute. So what that means is we do need to test the original. All right, so let's go up to our original. We see our alternator. So we know that it is an alternating series. So let's use our alternating series test. So let's look at the limit as n approaches infinity of the rest of that. So 1 over root n. All right, or n to the 1/2, doesn't really matter. As n gets larger and larger, that denominator gets larger and larger. So the value of that whole deal equals 0. That means, according to our AST, that the original converges. That's by AST. So we've got what's going on here? Clicky? Whatever. It's not letting me change. Whatever. All right, we've got absolute value, which diverges. We've got the original, which converges. So that means our original. All right, again, we were looking for converges absolutely, converges conditionally, or diverges. All right, so our original series that we were given converges conditionally. All right, so that alternator is what helps it to converge. Without it, the series diverges. Why is that letting me change my pen? Whatever. Purple it is. All right, part B. Infinite series -1 to the n plus 1 over 3n. Again, let's do the same thing. Let's check. We see that this is alternator up here. So let's check and see if that series, if we take the absolute value of that, let's see if it converges or diverges. Okay, so that takes the alternator out. So we're left with 1 over 3 to the n. That looks like a geometric. If we rewrite it in that form, that's the same thing as 1 over 3 all raised to the n power. Excuse me, so that means our r value is 1/3. In a geometric series, if the absolute value of your r is less than 1, then what does that mean? That means that it converges. All right, and we use the geometric series test to show that. So since the absolute value of our original converges, then that means we don't need to test the original. We can go ahead and say, man, I really wish I could change. I broke it. We can say that the original, well, let's just go back over here. The original converges absolutely, or is absolutely convergent. Absolutely. All right, awesome. Last topic. This is a great topic that kind of ties into some of the things we're going to do with the rest of this unit. It says alternating series remainder. If an alternating series satisfies the conditions of the AST, namely that the limit as n approaches infinity of a sub n equals 0, and the sequence a sub n is not increasing, and the series has a sum s, then the absolute value of r sub n, which is a remainder, equals the absolute value of the infinite sum minus the partial sum, which is less than the next term in the series, a sub n plus 1, where s sub n is the nth partial sum of the series. In other words, I'm right here, by the way, if an alternating series satisfies the conditions of the AST, you can approximate the sum of the series by using the nth partial sum s sub n. This is pretty cool. This is going to be useful. It's going to save us a lot of work. And your error will have an absolute value not greater than the first term left off a sub n plus 1. This means the absolute value of s sub n minus r of n is less than or equal to our actual infinite sum is less than or equal to that partial sum plus the remainder, absolute value of that. Okay, so what does that mean? That was a lot of words, a lot of symbols, a lot of variables and abbreviations. So let's look at what that means in these two examples. All right. They're both similar but slightly different. So example 3, approximate the sum of the infinite series here by using the first 6 terms and find the maximum error. Use your result to find the interval in which s must lie. Okay, so they ask us essentially to do 3 things. To approximate the sum, we're going to find the first 6 terms, we're going to find the maximum error, and then we're going to use that to find the interval in which our actual sum must lie. Okay, so first thing we want to do, we want to just start listing out more than this number of terms right here. All right, we need to go out at least one more than that term right there. So let's see how far I can go. All right, so from 1 to infinity. We don't have time for infinity. We'll just go out, like I said, 6 or 7 or 8 terms. All right, our function is -1 to the n minus 1 over n factorial. Am I reading that right? Yep. All right, so first term. If I plug in a 1, my power there, 1 minus 1 is 0, so that means this is just a plain old 1. 1 factorial is just 1. So that's a 1. And then we've got plugging in a 2. Our second term, 2 minus 1 is 1, so we're going to get a minus with a 1 on top. 2 factorial is just 2. I might, let's see, for space sake, I might just go ahead and leave these as factorials. Yeah, so next one's going to be 1 over 3 factorial minus 1 over 4 factorial. Those factorials start growing pretty quick, like, plus 1 over 5 factorial. These types of problems are, in general, calculator active problems. All right, there are ways to ask them on a non-calculator part, but when we're doing these approximations, we'll be using our calculator some. All right, so you see how this trend is going. We're adding, we're subtracting 1 over n factorial, and so on. We'll go out to the 9th one just for fun. And then again, it's just going to subtract the next one, add the next one, and so on to infinity. So what they ask us to do is to approximate the sum. Well, what we just read in this box was that if we find the nth partial sum, then that is our approximation of the sum. All right, we recognize that this is an alternating series. This only works for alternating series. All right, so there's our alternator. Okay, so let's pick out those first 6 terms, which is easy since our denominator is just n factorial. All right, so if we were to look at this partial sum, that's really s sub 6, all right, because we're looking at 6 terms. That's going to be our approximation. All right, if you add that up, either find common denominators or put it in your calculator, you're going to find that that is the fraction 91 over 144, which rounds to 0.6319. All right, so that's our approximate sum of the whole series, the whole infinite series, just by looking at those first 6. Because notice that why this is happening, if we look at each of these terms, as that n gets bigger and bigger, it's only getting bigger in the denominator. So each of these successive terms are getting smaller and smaller and smaller, so they're having less and less effect. And they're alternating. We're adding one, then we're subtracting the next. So we're putting a little bit more on, but then we're taking a little bit less off, a little bit less on, a little bit less off. So this is our approximation. All right, that's our approximate up here. All right, s sub 6, which is 91 over 144, approximately 0.6319. All right, so next up, they asked us to find the maximum error. Well, that maximum error, according to this, is the next term. All right, not our next sum, but just our next term. So looking at our sequence here, our next term is 1 over 7 factorial. So that's the maximum error. That tells us how good our approximation is going to be. It's going to be within the bounds of this plus this and our approximation minus this. All right, 7 factorial is 5,040. All right, and if you put that in your calculator, you get some scientific notation, which we got 3 zeros and then 198. All right, so really small. So what that says for me is that this is a really good approximation. All right, it's within 2 tenths, hundredths, thousandths, 10 thousandths, 2 10 thousandths of a unit. All right, that's pretty good to me. All right, so then it says, third thing, use your result to find the interval in which our actual sum must lie. All right, so that's what this piece says right here at the very end, last statement in our box. So all we need to do is say, all right, so our sum S, let's see, where do we have space for that? Let's go over here. All right, is going to be less than or equal to and greater than or equal to two values. And those two values are just going to be our sum. I'm going to use these fractions here instead of the decimals. Our approximation plus our error. And please don't worry about combining those into one term unless the directions say so. And it's got to be greater than our approximation minus that error, because that maximum error just says it can be plus or minus this much from our 6 partial sum in this case. All right, that's a minus there. All right, so there is the interval where our sum must lie. And again, we saw how small this is. So that's a really small interval. Really good approximation. All right, great. Let's look at our last example. Example number 4 says approximate the sum of the infinite series of -1 to the n plus 1 over n to the 4th with an error less than 0.001. All right, or 1/10 hundred thousandths, 1,000th. Okay, so this one essentially only asks us for one thing, to approximate the sum of this series. But let's start it out the same way. So let's say sigma from 1 to infinity of our rule. And again, let's list out our terms. The thing is, they don't tell us how many terms to go to directly, but they do indirectly. They say with an error less than 1/1000th. So remember, that error is the first term after the partial sums that we're going to use for our approximation. So when we find a term that is, in this case, less than 1,000ths, then we can stop, and we're going to take the partial sum before of all the terms before that term. All right, so what does that look like in this problem? Well, let's go ahead and start listing our terms, and we'll kind of check each one. So 1, plugging in 1. 1 plus 1 is 2, so it's going to be even. Power, it's going to be a positive 1. 1 to the 4th is just 1. That's just 1, really. Plugging in 2, that's odd, so it's going to be minus. 2 to the 4th power is 16. You could do this with decimals or with fractions. I'm going to kind of, along the way, I've already calculated these as decimals and just kind of write them underneath just so we can kind of eye that as we go along. Again, alternating series, so we're going minus plus. Our next one is going to be 1 over 3 to the 4th power, which is 81. 1 over 81 rounds to 0.0123. Next term is going to be minus 1 over 4 to the 4th power, which is 256. 1 over 256 rounds to 0.0039. So you see how we're getting closer? We're getting smaller and smaller values. We're looking for when we hit a term that is less than this. All right, so we essentially want 0, 0, 0. All right, as our first 3 numbers past the digit. We've got 2. It's going to be the next one. Let's see. 1 over 5 to the 4th power. 5 to the 4th is 625. 1 over 625 is 0.0016. Not quite. So close. So close. All right, but it's going to be the next one. Over 1 over, what is that? 1, 2, 3, 4, 5, 6 to the 4th power is 1,296. 1 over 1,296 is 0.000. There it is, 77. All right, that number is less than 0.001 that we were given up here. Also, again, this is just one, like we said, 1 over 1,000. We could have just looked for when we got bigger than that. But either way, this is one term too much. So what we're going to be looking at is what is the sum of these terms here. All right, this is going to be our estimate, our approximation of our sum. And we know because this is the next term, all right, this is the a sub n plus 1, where our n in this case is 1, 2, 3, 4, 5. Let's see if I can get rid of that. So we're summing up the first 5 terms. This is our 6th term. So this is a sub 5 plus 1, which just means it's, again, the 6th term. All right, so when you add those up, definitely a calculator part, it's going to be 0.9475, and we know that has an error less than this 1 over 1,296. All right, let's make sure we answer the question. Approximate the sum. That was this here with an error less than that, and we did that. All right, so that is it for alternating series for now. Again, we looked at our last test, alternating series test, making sure that we pick out that alternator, acknowledge that it's an alternating series, and then evaluate the limit. Again, only shows that an alternating series converges. We'll never use that for a divergent series. Make sure you try these 2 in your notes. We'll talk about them when we meet next. And then we also talked about the 2 types of convergent series, how to determine when a alternating series converges conditionally versus absolutely versus diverges. And we looked at our first dive into approximating series with partial sums and minimizing the error.